Hello, I'm Professor Daehn, Director of the Impulse Manufacturing Lab at Ohio State. The purpose of this short video is to give an introduction to the exciting techniques that we are developing here at Ohio State between my students and staff here, and we hope to really develop attention to these, and should you want to collaborate with us, please give me or anyone in my group a call, and we'd be happy to work with you. Much of the series is going to go through things in much greater depth than this initial presentation. This slide indicates really our motivations. Energy use and carbon production are really key problems for the human species, and about a third of our energy use is in driving vehicles of various sorts. If we can make lighter, more fuel-efficient vehicles, we can combat that. About another third comes from industrial processes, basically making and shaping materials. We think we can have important positive impacts in reducing energy use in both these areas. Well, this slide shows overall what we really do. This web page is going to go through all of these techniques in much greater depth, and we'll step through those one by one and give great detail. But I want to give a brief overview. One of the things we came across in the 90s is we found that we could really enhance formability by using processes at high strain rates. That means we can make more complex shapes. We can also induce residual stresses in an intentional way, so we can lock things together and join dissimilar materials by conformal joining. This is used commonly in the aircraft industry, not used too commonly right now anywhere else. We think there's a great future in that. We'll talk about that more later in other videos. Collision welding, if you get things to move together at very high speeds, you can actually cause the two materials to jet off their initial surfaces and form very interesting microstructures that allow you to grip together very dissimilar metals without causing any intermetallic formation or brittle phases. We can develop really high pressures as well. Those pressures can be used to put really, excuse me just a second, keep the current thing the same. So we can use those really high pressures to emboss one surface into the other, develop really very minute features with that. It's very exciting. We can also use that to do cutting processes, and we'll talk about that in some detail. We and others have shown you can do precision shape control with this. Basically have a net shape tool, cause high strength material to exactly form that shape. We can develop very light systems for flanging and hemming. We'll detail that later. Shock hardening is also possible. And then we'll talk a little bit about this today and elsewhere. The equipment to do this is also very light, very agile. That's very exciting. So the next slide indicates really the tools that we use. There's been a lot of work over the years on electromagnetic forming. We use that here as well. We'll talk some about that. There's also been work in a number of places on high-speed presses. The innovative fastener company Buhlhoff uses to insert nails at high speed, for example. That could be very interesting for putting dissimilar materials together. But there's a few things that are fairly special at Ohio State. First of all, we've developed a technique using vaporizing foil actuators, where we take a piece of aluminum, run a very large current through that all at once. We can vaporize this small area and develop very high pressures. We can also develop very high pressures at lower energies with a pulsed laser. We'll have videos associated with that. And then both of these techniques are able to get sheets moving at a speed of about 1 kilometer per second, really high speeds, 2,000 miles per hour in that kind of ballpark. Well, what we can do with that is do all of these processes, and it's important that we measure the speeds. Laser velocimetry gives us the tools to do that, and we'll talk about that in some depth also in this series. So the big question is, why do we use high-speed processes? Well, the two things, and we'll talk about these in great detail in the other videos, new operations are basically possible. And then the other thing that's really important is, don't show that message again. The other thing that's really important is the equipment can be very light. Once you have a capacitor bank that looks about like the size of a washing machine or a freezer, what you can do is hook that up to something very small, develop very high pressures on the order of a gigapascal over regions that can give you the same sort of forces you might be able to get off of a many 100-ton press. So we can really reduce the footprint of the equipment. Well, with these very high speeds, very interesting things happen. I'm going to focus a little bit right here on welding. And this is something we do with laser impact welding with the very fast laser process I mentioned. We can get a sheet of aluminum fairly thin, moving at about 1 kilometer per second over a region like that. This is the weld. If we actually peel this 5/1000th of an inch thick aluminum tab off, what we're left with is this area that's actually adherent to copper beneath it. If we take a section through where that line shows, you see a structure like this, where you see the aluminum stuck on the top. You see the copper beneath that's been hit so hard we've developed spalling in it. And then you have regions like this where there's actually welding. Here's what the welding looks like. If we zoom into a region like this, we see even where it looks very discrete, if you look at it with an electron microscope, as my great student Yuan Zhang did, you can see that there's an area that you see something that looks like there's mixed material, very fine grains, but this could actually have very good toughness associated with this. So it's a very different way we can do welding. So that works very nicely for small things. If we use our vaporizing foil actuator technique, we can get things 1, 2, 3 millimeters thick, flying at about a kilometer per second. If we do that, we can get these very interesting interface structures. What we have down here is titanium, and we've got copper up top, and you can see the wavy interfaces that we're able to make on small scales. This can be used for dissimilar metal joining for many types of metals, and we have a nice program for the Department of Energy to look at this over large numbers of materials that we're working on right now. Also, we can use this to drive material into single-sided dies. We can do shearing, forming, all in one operation, and it turns out the shearing, we get superior properties to what we get with traditional die shearing. Again, we'll talk about all of this in greater depth, and we can also shock harden the material, which is also quite interesting. So this is sort of an overview of what we can do. These are the methods that are out there for using high speeds. Explosives have been out there for a long time. We don't use explosives here at Ohio State for obvious reasons, but we can use electromagnetic forming, the vaporizing actuator technique, and laser impulse techniques. These are all things that are practiced here, and the two that are special at Ohio State are really the laser impulse, which is very close to laser shock peening, if you know about that, and the vaporizing actuator technique. Then there's a lot of things you can do with that. Those are mentioned here. You can enhance formability. We can do conformal joining, impact welding, embossing, cutting, precision shape control, flanging, hemming. Not all methods go with all operations, but they all have in common that you can improve formability, have lighter equipment, and do operations that otherwise are difficult to impossible. And we'll go through that in greater depth in this whole series. So here's the most important slide. I've got a great team of people that makes this happen. Postdocs, senior people in the group right now include Anupam Vivek, Jeff Tabor, Jason Johnson, and then we have great people that help us fund this work. Alcoa Foundation, Sandia National Labs, and Department of Energy are prominent among that group. So I invite you to enjoy what's here. Hopefully you learn from it. We hear from you on the video or on the website. In each case, what we plan on doing is there'll be a video and then archival publications and theses that are related to the video. We'll give you much more depth. We think this will be a very productive way that you can learn about the technology. Look forward to working with you, and thanks for watching.